KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we start with one example problem related to the information what we discussed in our previous class. And after completion of this, we will go to discuss Earth satellites. Okay, right. See here, ma. First, one example problem. That is what example 8.4. Two uniform solid spheres of equal radii. Two uniform solid spheres of equal radii, capital R, but mass capital M and 4 capital M. Right. So it is capital M and it is 4 capital M. Have a center of separation. Have a center separation 6R as shown in figure 8.10. That is what 8.10. Okay, right. Now this is what picture ma. It is 8.10. I didn't write the number, but it is the picture. The two spheres are held fixed. The two spheres are held fixed. Right. A projectile of mass small m is projected. A projectile of mass small m is projected from the surface of the sphere of mass capital M. Projected from the surface of the sphere of mass capital M directly towards the center of the second sphere. I will repeat once again. The two spheres are held fixed. Right. A projectile of mass m is projected from the surface of the sphere of mass capital M. This is the capital M. Directly towards the center of the second sphere. Right. Obtain an expression for the minimum speed v of the particle so that it reaches the surface of the second sphere. Right. So very interesting question here. As simple as such, there are two spheres, there are two solid spheres which are fixed to their positions, and after that, the mass also distributing within the sphere uniform. That is what he is saying. Two uniform solid spheres of equal radius, but mass is different. Mass distributed uniformly. Suppose the mass of this particular sphere is capital M, so it was distributed uniformly. The mass of this particular is that is what 4 capital M, so it is 4 times in mass when compared to this, right? So here also mass distributed uniformly. It is 4 capital M. Two uniform solid spheres of equal radii is a capital R and this is also capital R, but mass this is what capital M and this is what 4m. Have a center separation 6 capital R. Have a center separation 6 capital R as shown in figure. That is what 8.10. Right, in this figure. Now the two spheres are held fixed. Okay, that's what I already told you. A projectile of mass m is projected. Okay, so a small projectile is going to project from this sphere from here onwards. Right, that is projected from the surface of the sphere of mass capital M directly towards the center of the second sphere. Towards the center of the second sphere. Full stop. Obtain an expression. Obtain an expression for the minimum speed v. Obtain an expression for the minimum speed v of the particle. V of the particle. Okay, right. Full stop. Right. That is what so that it reaches the surface of the second sphere. Obtain an expression for the minimum speed v. Obtain an expression for the minimum speed v of the particle. V of the particle so that it reaches the surface of the second sphere. So that it reaches the surface of the second sphere. So throughout this discussion, throughout this questioning, what he is expecting? He is expecting the expression for the minimum speed of the particle which is going to throw from this, that is what, from this capital M, so that it will reach the surface of the second sphere, surface of the second sphere. Okay, right. Now see the answer. The projectile is acted upon by two mutually opposing gravitational forces. The projectile is acted upon by two mutually opposing gravitational forces of the two spheres. That is what you know very well, when two spheres are held, when two spheres held are separated by certain distance, automatically the gravitational force of attraction, that is what I can calculate by using the formula Gmm by r square, right? G, capital M, small m divided by r square is a general formula. Okay. See, the projectile is acted upon by two mutually opposing gravitational forces of the two spheres. So whatever the projectile which is going to thrown from this particular uniform solid sphere, which is going to experience or which is going to affect by the gravitational force due to these spheres and due to these spheres. Okay. So that is only he is saying. The projectile is acted upon by two mutually opposing gravitational forces of the two spheres, the neutral point n is defined as, see here, this is the neutral point. The neutral point n is defined as the position where the two forces cancel each other. The neutral point capital N is defined as the position where the two forces cancel each other exactly. If On is equal to capital R, right? So you please try to understand the information what I am giving, right? So I already written there, I have already written here, but at the same time I am also saying, so the particle, the projectile what is going to throw from here is going to affect, is going to experience the gravitational force by this mass and by this mass. Okay, that only I want to say. But after that, you know, when this force is equal in magnitude and opposite in direction, there you can experience, there you can expect a neutral point. That is what the neutral point n is defined as the position where the two forces cancel each other exactly. If On is equal to small r, we have, okay, right. That is what he is writing, Gmm by r square. So this is the point capital small r, no, right? This is the distance small r, no. So because of this, that is what gravitational force is, capital G, capital M, small m by r square. That is equal to 4 Gmm by 6r minus r whole square. This is what 6r. That is the distance between the center of mass of these two spheres, and it is the distance of the neutral point from center of first sphere, capital M, right? Now this is what this distance is nothing but 6r minus small r. This distance is nothing but 6 capital R minus small r. 6 capital R minus small r whole square. So capital G capital M small m divided by small r whole square is equal to 4 into capital G into capital M into small m divided by 6r minus r whole square, right? So this one will get cancelled. Finally 6r minus r whole square is equal to 4r square, and you know mathematically this you can write it as 2r whole square. So square will get cancelled. 6r minus r is equal to right? So what is 6r minus r is equal to plus r minus 2r, So finally you can write r value as either 2 or 2 capital R. There is a difference between small r and capital R, don't confuse. Capital R is in terms of, that is what radius of the sphere and the distance between these two spheres, but small r is the distance of neutral point from the center of mass of the first sphere. Okay, So small r is equal to 2 into capital R over R minus 6R minus 6R. Small r is equal to 2 into capital R over R minus 6R, right. See here, the neutral point small r is equal to minus 6R. Minus 6R does not concern us in this example. The neutral point small r is equal to minus 6 capital R does not concern us in this example, full stop. Thus ON is equal to capital R, small r is equal to 2R, because small r is equal to 2R means that is also equal to ON. No? See here, ON is equal to small r is equal to 2R. This value we can't take. Why we can't take this value? The neutral point R is equal to minus 6R does not concern us in this example, because how can we take minus 6R means it will come like this, right? Minus means negative x-axis. So it is nowhere related. That's why we have to take this value. It is sufficient to project the particle. It is sufficient to project the particle, right? It is sufficient to project the particle with a speed which would enable it to reach capital N. Which would enable to reach capital N, full stop. Thereafter, the greater gravitational pull. Thereafter, the greater gravitational pull of 4 capital M. 4 capital M would suffice. That is what sufficient, right? Thereafter, the greater gravitational pull of 4m would suffice, right? The mechanical energy at the surface 4m would sufficient, right? Now, the mechanical energy at the surface of capital M is, this is what EI is equal to of mv square minus g mm by r minus 4 g mm by 5r. This is what mechanical energy at the surface of capital M. Mechanical energy at the surface of capital M. Okay, right. Next, at the neutral point capital N. See, I didn't write here, but I am saying, you know very well, this is the mechanical energy at the surface of capital M is. Okay. Now, at the neutral point capital N, the speed approaches to 0. See, at this point, at the neutral point capital N, the speed approaches 0. Right. The mechanical energy at N is purely potential. The mechanical energy at N purely potential. Why at N it is purely potential? Because when the speed becomes 0, then there is a energy possessed due to the position only, due to the speed we can't expect. That's why purely potential. So En is equal to minus g mm by 2r minus 4 g mm by 4r. Okay. See here. Now, from the principle of conservation of mechanical energy, that is what 1 by 2 v square minus gm by r minus 4 gm by 5r is equal to minus gm by 2r minus gm by r. R over r, v square is equal to 2 gm by capital R into 4 by 5 minus 1 by 2. So that v is equal to 3 gm by 5r whole power 1 by 2. Okay, right. See this. So here what can we say? A point to note is that, here is an important point to note down. That is, the speed of the projectile is 0 at n. The speed of the projectile is 0 at n. The speed of the projectile is 0 at n, but is non-zero when it strikes the heavier sphere 4 m. I will repeat once again, because this point is very important for us. We derive an expression, we obtain the expression for the minimum speed of the particle. It's okay, that is what v is equal to 3 gm by 5 capital R whole power 1 by 2. But here the important point is, the speed of the projectile is 0 at n, okay, but it is non-zero when it strikes the heavier sphere 4 capital M, full stop. The calculation of this speed is left as an exercise to the students, right? So this is what you can calculate by using related to 4 capital M, okay, right. Next continuation topic, Earth satellites. Okay, first you see here, You know, Earth satellites are similar like objects which revolve around the Earth. The motion of Earth satellite is very similar to the motion of planets around the Sun. And hence, Kepler's laws of planetary motion are equally applicable to them. So, how Kepler's laws of planetary motion are applying to the planets? Similarly, Kepler's laws of planetary motion you can apply for Earth's satellites. Okay, now, in particular, their orbits around the Earth are circular or elliptic, right? Moon is the only natural satellite of the Earth with a near circular orbit with a time period of approximately 27.3 days. 27.3 days, which is also roughly equal to the rotational period of the moon. So, the time period approximately 27.3 days. So, this time period is for what, ma? This time period is for moon. Moon is the only natural satellite of the Earth with a near circular orbit with a time period of approximately 27.3 days, which is also roughly equal to the rotational period of the moon about its own axis. Okay, right, full stop. Since 1957, advances in technology, right? So, from 1957, advances in technology have enabled many countries, including India, to launch artificial Earth satellites for practical use in the fields of like telecommunication, geophysics and meteorology. Okay, this is what application of Earth satellites. Okay, right. Now we are going for some mathematical process, or we are going to express, or we are going to derive an expression for speed, and we are also going to derive an expression for time period. Okay, see this. We will consider a satellite in a circular orbit of a distance RE plus h from the center of the Earth. You know very well, for example, it is the Earth, ma. So, it is the center of the Earth, no? Suppose it is the Earth. It is the center of the Earth. And the satellite is revolving here, no? When the satellite is revolving at certain height from surface of Earth. So, what I am saying is, we will consider a satellite in a circular orbit. Of a distance RE plus h from the center of the Earth. Okay, full stop. See here, the centripetal force required for this orbit is F centripetal is equal to, you know the formula mv square by r. In place of r we have to write re plus h. So, F centripetal is equal to mv square by re plus h. It is like equation number 1. And here re is the radius of the Earth, and small m is the mass of the satellite. And v is the speed of the satellite. Now, then the centripetal force required for this orbit is F centripetal is equal to mv square divided by re plus h. Directed towards the center. Okay. The centripetal force is provided by the gravitational force. This centripetal force is provided by the gravitational force, which is see here, F gravitation is equal to capital G small m into capital ME divided by RE plus H whole square. That is what equation number 2. Okay, right. Now, it is like equation 1, it is like equation 2, equating RH's right hand side from equations 1 and 2. That is V square is equal to GME by RE plus H, because here M by RE plus H will get cancelled. This term and this term we are going to equate, means by after completion of the cancellations, here it is V square is equal to GME by RE plus H. I hope you understood here. This is what this one is going to equate to this one, and small m by RE plus H. Small m by RE plus H is become equal to this is what a small m v square by re plus is equal to g small m capital M e by re plus h whole square, and small m will get cancelled and re plus h will get cancelled. So finally it is v square is equal to capital G capital M e divided by re plus h, that is equation number 3. It is the expression for square of the speed. Now thus v decreases as h increases. Thus v decreases as h increases because it is inversely proportional. No? Inversely proportional. Okay, right. So this is what this is what v decreases as h increases. From equation 3, from this equation, the speed v for h is equal to 0. H is equal to 0 means what? Ma? That is almost nearly equal to the surface of earth. So then v is equal to, that is gm by re. Gm by re. You know already the expression for small g, that is gm by re square. No? So if you are writing this in terms of small g, then the speed of the satellite close to the surface of earth will become equal to small g capital re. Okay, right. Now see here, that is what where we have used the relation. Okay, right. In every orbit the satellite traverses a distance 2 pi into re plus h. You know very well, ma, that is the circumference of the circle. Circumference of the circle. Okay, the satellite traverses a distance 2 pi into re plus h with the speed v. Its time period t therefore is, its time period capital T therefore is capital T is equal to, capital T is equal to 2 pi into re plus h by v. That is equal to, see already we got v value here, that v value you have to substitute here. Ma. So if you substitute v value here, then you are getting 2 pi into re plus h whole to the power of 3 by 2 by square root of gme. Okay, gme, right? Okay. On substituting the value of v in this expression, we are getting, this is the expression for a time period. Okay, and here if you observe carefully, t square is equal to k into re plus h whole cubed. So these are all k. Re plus, these are all like constant, no? G is constant, mass of earth is constant, and 2 pi is constant. So if we replace all these things with k, that is what t is equal to k into re plus h whole power 3 by 2. So now we can write, we can say here t square is equal to k into re plus h whole cube, where k is equal to 4 pi square by gme. Whereas Kepler's law of periods as applied to motion of satellites around the earth, as applied to motion of satellites around the earth, full stop. For a satellite very close to the surface of earth, small h, for a satellite very close to the surface of earth, small h can be neglected in comparison to re. That's what I already told you here, no? Okay. And one more thing he is saying is that small h, the height of the satellite, when it is very close to the surface of earth, can be neglected when compared to the radius of the earth. Then for such satellites, t is t naught. Then what can we write? T naught is equal to 2 pi into square root of re by g. So if you substitute the values, that is re is 6400 kilometers. Otherwise, if you want to know in meters, 6400 into 10 power 3 meters, because 1 kilometer is equal to 1000 meters, no? Right. So T naught is equal to 2 pi into square root of re by g. For earth, T naught is equal to 2 pi into square root of 6.4 into 10 to the power of 6 by 9.8. If we complete this calculation, you are getting approximately 85 minutes. 85 minutes, that is the time period according to this expression. Okay, right. So this is all about the example problem and earth satellites. Okay, right. In our next class, we will continue with next continuation topic. Okay, thank you.